All right, let's take a look at section 1.2, relations. Okay, so this is going to be a really basic definition here. We're going to uh, make this more specific later on. We're going to have specific types of relations that we're going to call functions. But we're not quite talking about that yet. We're in complete generality here, just talking about relations. So a relation is just a set of points in the plane. We talked about the coordinate plane last time, so we just got a bunch of ordered pairs, right? So these are ordered pairs, right? Um, so uh, many examples, right? We can have an example. Look, here's an example. Boop, boop, boop. Here's some ordered pairs, bunch of points in the plane. I can draw a picture of it and show you, hey, here's a picture of a bunch of points in the, a bunch of points in the plane. Or we could also just directly list them, right? So maybe 1, 2, 3, 4, 5, 6, whatever. Just a bunch of ordered pairs, right? So it's a set. We know it's a set because of these curly brackets here, and we know that it's, well, the elements of this set are all ordered pairs, right? Later on, we might see this listed. Here, I'm going to draw the same relation written in a slightly different way. Later on, we're going to look at stuff that looks kind of like this, where we're going to end up calling all of the things that come first, we're going to call that domain, and we're going to call the things that come second range. But we're not quite there yet. We're going to call these things domain and range later on, but just a little foreshadowing. Here's another way we can express a relation. So great. So we can draw a picture. We can explicitly list ordered pairs in the roster method, right? So here's roster method. Or let's look at one where we're going to use the set builder. So let's start out with an easy one here. So maybe the set of all x, y such that maybe x is 2 and y is real. Now in the homework it might not list y is real, but it's just assumed y is any real number at all. If that's not written there. So if I have the set of all ordered pairs such that x is equal to 2, they just kind of assume that y could be anything. It doesn't really matter what y is. But if we write it, then it might be a little more clear to us how we find other ordered pairs that belong to this. So yeah, we got to find some ordered pairs that belong to this, right? So let's draw maybe a picture like we had over here. Okay. So any ordered pair that's in this set, we have to have x coordinate 2. And so we can make a list of some of these. So maybe 2, comma, and then y can be any real number we want. So, I could choose 1, that's in there because 1 is a real number. That's got to be in the set. Okay. Uh, we could have 2 and any other real number, right? 3, 2, 5. It doesn't really matter. 2, comma, any real number. So 2, comma, any real number is in the set. Well, if I want to draw a picture of this, let's draw a picture of it. So 2, 1 is in the set. Boop. 2, 3 is in the set. Boop. 2, 5 is in the set. So it looks like if I drew all of these and any real number, so I could put 1 here, 1 here, 1 here. I could put infinitely many of these things on here because there are infinitely many real numbers, right, for the choices of y. And when we put enough of those on there, we're going to have a solid line here. And lo and behold, we've drawn a picture of a vertical line. Look at that. So notice that we had x equal 2, and when we drew a picture of that, it was a vertical line that went through the point 2, 0, right? So let's look at another one that's kind of like that, but it's slightly different. So let's sketch the set of all x, y such that y is -1. Okay, well, we can do the same thing here, right? So what's in this set here, or we're going to have any real number for our x value, and we're going to have -1 for our y value. So any element of this set looks like this. Well, just like we did for this other example, we can just plop a whole bunch of ordered pairs on there, right? If y is -1, I can pair any real number value for x with -1. So I could put 0 with it, I could put 1 with it, I could put 2 with it, I could put a half with it, 3/4, we could put that in there, we could put 1/4. They're all going to be all these dots on that line, y equal -1. And lo and behold, hey, we notice that this is a horizontal line, right? Maybe I can write this. Okay, so that's great. And what we can do here is we can sort of generalize what we're doing, and that is written right here. So if I have any equation that's of the form x equals something, that's going to be a vertical line, right? So if I have a here, any ordered pair that belongs to this is going to have x coordinate a, and there's infinitely many of them, so we can draw a solid line. And similarly here, y equal b is going to go through the point 0b. Okay, so let's maybe do an example where we're going to do the same thing we did above, but it's going to be a little more difficult, because let's use an inequality. So let's have the set of all xy such that y is less than 5. Okay, so we know that y equals 5 is horizontal, right? So if we wanted to start drawing a picture of this, we've got y equal 5 is horizontal, 1, 2, 3, 4, 5. So we're going to have something to do with this line. So we don't have any restrictions on x, so that means x can be any real number at all, but our y values just need to be less than 5. So here's where y is equal to 5, and we just want everything below that, right? We got to be less than 5. So we're going to shade in everything in here. And in WebAssign, there's a little tool, I think it looks like this. It's like a little paint can or something, and that's going to fill a region for you on WebAssign. So you'll have to draw a dashed line to indicate that there's a boundary, and it's dashed here for either a less than symbol or a greater than symbol. Now it's going to be solid if we're going to have the non-strict inequalities. Let's do an example real quick that has non-strict inequalities. So maybe the set of all x, y such that, let's make it a little bit more complicated. Let's say y is less than 5 and -1 less or equal to x less or equal to, say 3. Okay, so now we have that y has to be less than 5. So let me switch colors here. So this, we got y equal 5 is horizontal. Now we have boundaries on the x as well, right? So x equal -1 here is going to be a vertical line. And then x equal 3 is also vertical. Now with these, we can have -1 equal x. When we're drawing our picture, we're going to have the same restriction for our y values. We've got to be all below all of these. So maybe in our work on paper, we can put little arrows on there. And then we have to worry about our restrictions on x. So x equal -1 is vertical, but it can be equal, right? It's less or equal. So for this one, we're going to use a solid line. So we got a solid vertical line here at x equal -1. And we got a solid vertical line at x equal 3. And we know that our x values have to be between there. So maybe in our work, we can put little arrows here to say, hey, where we're going to shade. So we have to be below the line y equal 5. And we have to be between these other two values. So we would draw 3 lines there, and we can shade the appropriate region. All right, cool. So there's a couple examples of that. How wonderful. So this is kind of something that was a little bit glossed over fundamental graphing principle. So the graph of an equation is a set of points that satisfy the equation. So what this means here, this means that we can plug in the point and it gives us a true statement. Okay, so for this one is the point 2,1 on the graph of this equation here. So just, I guess, to be clear, the graph of this thing, we could, if we wanted to, we could write it like this. In step builder notation. But when we say, the graph of this equation, it's assumed that we're talking about a set of ordered pairs, right? It's a set of points, so it's a set of ordered pairs that makes it true. So it's the set of all x, y, such that that's a true statement. So what we can do is we can plug 2,1 in there. So, and see, hey, does it make it true? So we're going to put in 2 for x, and we're going to put 1 in for y. So we're going to put that right there, and we're going to put that right there. And we can do this. This hopefully is routine here to plug this in. So let's do that. So we've got 2 in for x, so I got 2 squared plus y minus 1, and I should have written a 1 in there for y squared equal 4. And then that simplifies to 4 plus 0 equal 4, and that's true. So then we conclude that 2,1 is on the graph. So there's not really an example of something that's not on the graph, but you're just going to come up, in this step, you're going to come up with a false statement. So you'll write something like, 2 is 3 or 0 equal 5 or something like that. So great, we can just plug in the number and say, hey, does it make it true? Okay, so these aren't going to be, this is not going to be the flavor of these exercises. They're not going to say, hey, is this point on the graph? They're going to say, give us all the points, or they're going to say, draw a complete graph, or something like that. So instead of just checking one point over and over and over, we're going to want to find all of the points on a graph so we can draw the picture. So we want to sketch a graph. So let's look at this one here in a second. Let's do an easier one first. So let's draw the graph of maybe y equals x plus 2. Okay, so what we can do here is we can just pick values, any values, because there's no real restrictions here. We just have to, now I don't want to complicate things, but when we think about it as a set of ordered pairs such that this thing is true, x and y are assumed to be real. So what we can do is we can just do what we did with those other ones, right? When we came up here, right, for this one, I knew that x had to be 2. So for any, I just picked, for any y value, the x was going to be 2. So we just kind of plucked these values out of the air, just picking out real numbers. So we can do the same thing with this example here. Usually we will make a nice little chart and we'll have x values that we'll just choose. And we know that the y value has to be x plus 2 for any of these things. So we can pick an x value, your favorite real number. Usually we want to say that our favorite real numbers are easy. So we want to maybe stick around the easy ones, -1, 0, and 1. And then we can just plop the x in there and see what y has to be. So y has to be, well, -1 here for x plus 2. So that's going to be 1. Here we're going to have y equals 0 plus 2. So that's going to be 2. And then this one we're going to have y equal 1 plus 2, which is 3. So this gives us ordered pairs, right? X, y. And we can write them as ordered pairs, -1, 1, 0, 2, 1, 3. So there's not really anything special about -1, 0, and 1 other than they are easy. So pick easy values, or maybe a better word for that instead of easy is convenient. So maybe we can choose numbers that'll make it so we don't have to deal with fractions. So, for example, maybe I have a 3 here. So then I would, or excuse me, that wouldn't be too tough. Maybe I have a 1/3 here, right? Then maybe I might want to choose x values that are multiples of 3 so that my fractions all cancel out. So long story short, pick convenient values, things that are going to make your life easy rather than hard or difficult. Okay, so let's do let's sketch a graph of I forget what I'm trying to say here, the previous example. So we had x squared plus y minus 1 squared equals 4. I think we already found that 2, 1 was on the graph. Okay, we already knew this. That's great. So what we want to do here is find numbers that, or excuse me, find ordered pairs such that this relationship is true. Well, one of our difficulties here is that this does not look like what we had up there. The one up here was far simpler, right? It was already solved for one of the variables, and that was convenient because we didn't really have to rearrange stuff. Now I can go and I can pick. I can do the same task here. I can pick anything I want for x. I can just plug it in and solve for y, right? Now, rather than do that over and over and over, why don't we just rewrite this thing right off the bat, and we can solve for one of these variables. And then our life is going to be much easier. Solve for one variable. So again, we want to think about the easiest thing we can do here. So I think the easiest thing to do, or the quickest, would be to solve for this guy, right? But I mean, let's do the other way. Let's solve for y, because we usually want to write it as y. We want to choose x values and find y values. So let's do that. Let's solve for y here. So maybe this is a nice little review for our prerequisite stuff. Right? We can solve an equation that has a square in it. If I want to solve for the y, I want to get the y stuff alone. So our first step, we're going to subtract x squared from both sides. And then we're going to end up with y minus 1 squared equals 4 minus x squared. Okay. And now we can do that square root property, right, where we take a square root of both sides. Right, and we got to not forget about that plus and minus. Okay, so we got plus or minus square root 4 minus x squared. All right, and now what? We just add the 1. So we got y equal plus or minus square root 4 minus x squared plus 1. Okay, there we go. So now we can make our nice little chart. So here we go. We got x's, we got y's. And we know that y is going to be plus or minus this business. So 4 minus x squared plus 1. All right. All right, now that we've done that, let's get rid of this so I've got a little more room. Okay, so now our task is just to pick convenient x values so that we're going to get a good idea of what this picture looks like. So let's do that. Maybe if we can pick some convenient values, we can see what the picture looks like. So let's do that. Well, why don't we pick our buddies, right? If I pick -1, 0, and 1, would this be convenient? Well, if I put -1 in there, then my y is going to be plus or minus square root of 4 minus -1 squared plus 1. And we can do that. That's square root of 5 plus 1. So in turn, we have ordered pairs, right? So this is going to be -1 is going to go with plus or minus square root of 5 plus 1. Now, if we want to put this on our graph, that's going to be kind of inconvenient for us to do by hand because we're going to not exactly know where that is. We can sure approximate it. We can punch it into a calculator and get a decimal value. That's absolutely true. But for our practical purposes, we want something easier than this. We want a whole number, right? And we're going to see that we do get a whole number for this one. So plus or minus square root of 4 minus 0 plus 1. So this is plus or minus, what is this? Square root of 4 is 2 plus 1. So now our ordered pairs become 0 comma positive 2 plus 1. So that's 3. And then our other one would be 0 comma, then the negative 1. So negative 2 plus 1 would be negative 1. Okay, so those were convenient, right? Because they're whole numbers. So maybe we can try to pick other values that give us whole numbers, right? So maybe, and I hope we can see maybe what the goal is. If we can construct or figure out an x value to make this number be a perfect square, then that's going to be super convenient, and that's exactly what we want. So we've seen here that if I put a 0 in there, it makes it a perfect square underneath there, right? The perfect square 4. We can see if I put in negative 2 or positive 2, we're going to get a perfect square underneath there as well, right? 4 minus 2 squared, that's going to be 0. So we have y equal plus or minus 4 minus negative 2 squared plus 1. So this is going to be plus or minus 0 plus 1. So that's just 1, right? We got negative 2 comma 1. Okay, same thing with this one. Y is plus or minus square root of 4 minus 2 squared. Okay, plus 1. Well, that's just going to be 0 again. So we're going to have positive 2 comma 1. Okay, so at this point, we might want to start putting these points on a graph. So let's do that. These are going to be a little more difficult for us to draw, but we totally could if we had a nice little calculator decimal approximation for this, or we don't really need a calculator to do this, right? We know that 4 is less than 5, which is less than 9. These are the perfect squares that surround 5, right? So this fact implies that the square root of all these things have to be in order, right? So in turn, that says 2 less than square root of 5 less than 3. So we know that the square root of 5 is between 2 and 3, right? Okay, and we didn't have to use a calculator for that. How wonderful. Anyway, let's put these points on there. So we got 0, 3, 1, 2, 3, boop, 0, negative 1, boop, negative 2, 1, boop, 2, 1. And then we've got plus or minus square root of 5. So that's something between 2 and 3. Plus 1. So that would be something between 3 and 4. Negative 1. So wait a minute. If this is between 2 and 3, there's an error here. So let's correct it real quick. Hopefully the savvier of us have noticed that we made an error, and it's going to be really quick to fix. So it's okay. Okay, so the error was in that first step, this one, and it was right here, right? Because 4 minus negative 1 squared, that's 4 minus 1. So we need a 3 here, not a 5. So oops. But relatively minor error. And we would have seen, if we would have plugged in some more points, we would have seen our error because those ones with the square root of 5 would not have fit the pattern. So anyway, we can do the same thing for approximating what this is, right? 1 less than 3 is less than 4. So then the square root of 1 would be less than the square root of 3 would be less than the square root of 4, right? So square root of 3 is between 1 and 2. So that means -1 is paired with something that's like here and here, something between 2 and 3, right? And no. So I'm drawing those in the wrong way. That'd be down here. But anyway, we can plot some more points, and more and more and more. If I put in a 1, we're probably going to be over here, and the more and more points you put on there, we're going to see that it's a circle. Now my picture isn't exactly perfect, but we can sure draw nice pictures with the computer. Okay, so something that we should say a few words about is our choice of x values. It's not going to be true that we're going to get real numbers every time. So in particular, maybe we can pick something like maybe 3. So if I picked 3, what would happen? So we got y is plus or minus square root of 4 minus 3 squared plus 1. So that's plus or minus, oops. All right, so that's plus or minus 4 minus 9 would be -5 plus 1. And now this is not real. So we want to avoid values that are going to give us numbers that are not real. We're going to call this domain later. We hopefully know from previous coursework that we need radicands of even indexed radicals to be non-negative. This is going to come up later, but it's coming up right now. So, heads up, this is a thing. We need the radicands of even indexed radicals to be non-negative. So we know a square root, the index of a square root is 2. We just don't write it because it occurs so often. So in particular here, we need the radicand 4 minus x squared to be non-negative, so greater than or equal to 0. So any x value we choose must satisfy this, and that's kind of how we can start choosing what we want. So maybe we could take this one more step. If I come over here, we could say that 4 has to be greater than or equal to x squared, or x squared less or equal to 4. So this tells us what we need to choose. Any x such that x, the square of it, is less or equal to 4. Those are legal values to choose. Anything else is going to give us a number that's not real. We'll talk more about solving inequalities of this type later on, but I think we got the general idea at this point. Okay, so when we're drawing graphs, definition 1.5. So suppose a graph, an equation is given. Oh, great. We kind of touched on this in section 1.1. Intercepts are where the graph touches the axes. So it's not true that every graph is going to have x and y intercepts, but we are going to find x and y intercepts in the same way for every graph we've got. So let's fill these in. So finding intercepts of a graph from an equation. X intercepts have the form blank. So if I've got an x-intercept, a point on the graph which is also on the x-axis. So here's one right there. Here's another one, right? These are points on the x-axis. So we kind of want to just generalize what's true about all of these points, right? So this has y is 0, right? So does this. So does this. So does this. Wherever we're on the x-axis, y is equal to 0. So x-intercepts are going to have the form x comma 0, right? And anything that's on the y-axis for a similar reason, I guess, is going to have x coordinate 0, right? We're not going to move anywhere in the x direction, so x is 0 for all of these points right here, right? So we have 0 comma y is going to be the form of our y-intercept. Essentially, to find these, we're going to set, just like we did above with the little chart, we're just going to plug a number in and find out what the other one has to be. But here we're going to use a specific number. So we're going to set y equals 0 and solve for x. And to find y-intercepts, we're going to do the same thing, right? We're going to set x equals 0, solve for y. So we can have an example of this. Maybe we can do a little slightly easy example. So maybe 2x plus 3y equals 6. So x-intercepts, we're just going to set y equals 0. So we've got 2 times x plus 3, and then we're going to substitute a 0 in. And then we're going to say, hey, what's the x value have to be to make that true? So that times 3 times 0 is just 0. So we got 2x equals 6, and then we divide by 2, and we got x equals 3. So our x-intercept is the point 3, 0 for this graph. Wonderful. And we can find y-intercepts too. Set x equals 0 now. Okay, so we got 2 times 0 plus 3y equals 6. That goes to 0, so we got 3y equals 6. And then divide by 3, we get y equal 2. So the point 0, 2 is a y-intercept of this graph. Okay, great. Intercepts are wonderful tools to use for graphing. We're going to use these a lot throughout the semester, so we'll have plenty of examples of these. Okay, I think the last thing we're going to do here is symmetry. So we talked about symmetry last time, right? So let's draw a little picture down here. Recall that if I've got a point xy out here in space, a point symmetric to this about the y-axis is over here, right? We make the x value negative. We talked about this in the last section. A point that is symmetric about the x-axis is going to have the same x-coordinate but a negative y value. And the same for the origin, or similar for the origin symmetry, we're going to have negative x here, negative y. Okay. So testing a graph for symmetry, if we're just given an equation, we're going to substitute negatives in and see if we get an equivalent statement. So was that graph we just drew symmetric? It sure was, right? This one. It was symmetric about the y-axis, right? But not the x-axis. So let's, knowing what this graph looks like, let's use this as an example. So we have x squared plus y minus 1 squared equals 4. Okay, so we're going to test for y-axis symmetry. We're going to put negative x for x. And we're going to see if it's equivalent. So I'm going to put a negative x. Grouping symbols are going to be pretty important for us here. They're going to be a little frustrating for us, the mistakes that we make because of grouping symbols. So I would very much suggest we use grouping symbols wherever we can, because we're going to make less errors that way. Okay, so now I've got a negative number times x squared. So negative 1 squared, that's positive 1, right? So this is going to be a positive x squared. And this is the same. So that means that this graph has y-axis symmetry. Okay, and we're going to have to test the other symmetries too. So let me get rid of that. So let's test the x-axis. We're going to put a negative y for y and see what happens. So we're not messing with x now, but we are putting a negative y in for y. Okay, so it's going to be your temptation to distribute this, but that is not the way exponents work. Be very careful with this. We can just look at this on the face of it and say, hey, I'm comparing it to the original one, right? So I got x squared, that's great, but this stuff in here is different, right? If I would square all of this stuff out, and I mean, we can if we really want to, but we don't really need to because we can see that this is different than this, right? So when we see that they're different, we get a different result after we simplify it. We can say that this is not the same. So that tells us that there is no x-axis. symmetry. So we've got x-axis symmetry, y-axis symmetry, and origin symmetry. We're going to put negative x and negative y for x and y. So that's origin symmetry. Don't want to get too busy with the lines here. We got to separate stuff. So we just put negatives in for both, right? So I'm going to have negative x squared plus negative y minus 1 squared equals 4. So this part, pretty clearly not the same, but the x stuff is the same, right? So we got x squared plus negative y minus 1 squared is 4. So we would say no origin symmetry. Okay, let's maybe do one that's a little less complicated here. Yeah, so let's do a different one here. So maybe, or maybe we can make it complicated in a slightly different way. How about y equals x cubed plus x over x? Okay, so we don't know what this graph looks like, but we can sure test it for symmetry. We're just going to do the same thing we did for this other one. So if I want to test for x-axis symmetry here, whoops, I need to get back on the thing there. There we go. So if I want to test for y-axis symmetry, I'm going to put negative x for x. If I want to do x-axis symmetry, I'm going to put negative y for y. If I'm going to do origin, I'm going to put negatives for both. Put negative for both. Okay, we can do this. Maybe we just do them all in a line here. So put negative x for x. So I'm going to have y equals negative x cubed plus negative x over negative x. Okay. X-axis symmetry, I'm going to put negative y in for y. So I got negative y equal x cubed plus x over x. So at that point with this one, we're pretty clear that this is not the same, right? We got a negative on one side here. We don't have a negative here. We've got this stuff's all the same though. So we're going to say a big old no on that one. Origin symmetry. So we're going to put a negative for both. So we got a negative y in there, and then we've got a negative x cubed plus negative x over negative x. All right, now we've got a bit of simplification to do here. So let's go on the left here. So we've got y equals, if I cube a negative, it stays negative, right? So we got negative x cubed, and then plus negative x to be minus x, okay? And then we got negative x on the bottom. Well, we're already done with this one, so we're finished. We don't have to put anything else there. But this one, isn't that the same thing on both sides there? So we got negative y, and then we got negative x cubed minus x over negative x, right? Because we would have the same result. So now here's where the tricky part occurs, because we want to be done, but we're not, right? This thing can be simplified. We can notice that all of those terms have the same negative factor. So if we factor out a negative 1 out of the top, then our negatives cancel out, right? Our negative cancels out with that negative, so we just have x cubed plus x over x. And we look back to what we had to start with, and we say it's the same. So we say, yes, it does have y-axis symmetry. So maybe just to be, more clear, it's the same. That's for y-axis symmetry. Now for the other one, for the origin symmetry, we're going to have the same result on the right-hand side, but we're not going to have the same thing on the left, right? So we would say a big old no on the origin symmetry for this one, but it does have y-axis symmetry. So be careful with these, because sometimes we're going to have to simplify a fraction. All right. Anyway, that's it for section 1.2. So thanks for watching the video. If you have any questions at all about anything at all, please don't be quiet about it. Let me know. We can set up a time to meet either over Zoom or in my office if you're in Kearney. But yeah, have a great rest of your day.